It is time. It is time. I am going to attempt the impossible. The holy grail of statistics, as they say. So holy and so graily is this quest that many have tried, nobody succeeded. Because honestly, if people tried and succeeded, nobody else would try. What am I talking about? You know exactly. You know what I'm talking about. You know. You know. The thing that I am talking about is the double bind. The double binary. The double cat. The double category. What do you do when you've got two categorical variables and you're trying to assess their relationship? That right there, my friends, is the holy grail of statistics. And this isn't the first place you're going to hear it. In fact, let's go to ChatGPT. What is the holy grail of statistics? Turning uncertainty into actionable knowledge? No. Ultimate model or method? Bayesian statistics? No. Causal inference? No. The ultimate unsolved problem? No. Yeah. But
no, you're wrong. It's plotting two categorical variables.
So this is going to be tough. I'm just telling you right now. I'm going to put it out there. I'm going to make it as simple, as black and white, as plain as it can get. Just like the phrase that I just said. This may be the hardest plotting challenge I have ever accepted. Touché! It is the unofficial, practical holy grail. Oh, this is actually informative. Plotting two categorical variables in a way that is informative, not hideous, yes, and yes, not misleading, actually interpretable by normal humans. Yeah, because like anything that you look at, like a bar chart or a stacked bar chart or an association plot or a mosaic plot, like you have to do all sorts of mind bending to figure out what's going on, and it's really hard.
Contenders include stack bar charts, group bar charts, mosaic plots, dot plots, stack plots, getting better but not standardized, ugly and hard to explain, yeah, heat maps, sometimes useful but often visually overwhelming and ambiguous.
I've been doing this stuff professionally for 15 plus years. Who are you? And I still pause every time I have to plot two categorical variables. There's no universally great solution, and when you add missing data or low cell counts, it gets even worse. So yes, plotting two categorical variables is absolutely the practical holy grail. Anyone who solves it definitely will become a stats folk hero. And that's why I'm here, by the way. That is the reason that I am a stats guy, is because I'm here to be a stats folk hero. So that's what I'm going to tackle today. I'm going to try to solve that, and we'll see how it goes. So I'm just going to start with some brainstorming. Ideas. Well, I just did a bunch of things with binning. Binning? We did that with logistic regression, where we had a continuous x, and then at every level of x, we bend it, and then computed proportions. And oh, no, that's not going to work. Not going to work. Why? Because you can't bend something that's already binned. It's already a categorical variable. You can't bin it. All right, so our first idea has already failed. Binning. Wrong. X is already binned. Okay. Extensions of existing plots. So we've already got association plot, bar chart, bar plot, mosaic plot. So maybe we could do an extension to an existing plot. The other idea that I had that is maybe just crazy. What is it called? DHARMa. It turns a binary outcome into something continuous. And I don't know much about it. So DHARMa is this R package. DHARMa residuals are residual diagnostics for hierarchical, multi-level mixed regression models. Okay, so that's something we could look at. What other ideas do we have? Let's see what ChatGPT says. Here's some ideas I have so far. Investigate polychoric correlations. So the idea behind polychoric correlations, so you've got two ordinal variables of some sort, and your assumption is that the manifestation of those variables, the ordinal nature of it, underlying that is some sort of continuous variable. And so I wonder if we could use some of the ideas from polychoric correlations to try to do that. Any other ideas I can explore? Fit a Bayesian model and plot. Ooh, yeah. Bayesian posterior predictive checks. Oh, I thought of another idea. Added variable plot. That's actually a really good idea. So in the last couple of videos, I talked about a logistic version of an added variable plot. And the cool thing about those is once you fit the first predictor, then your residuals are either probabilities or logits, and you have a continuous variable. So you've taken a categorical variable and converted it into a continuous variable. And so I can see this working really well. So if you have a logistic regression with both a categorical and a numeric variable, you can use the existing plots that I've created to residualize things and then look at the categorical variable. So order of operations, residualize numeric first, then look at categorical. And that's cool. And that would work without like any modification on my part, which is great. But what if all your predictors are categorical? And I've had that happen before, where every single one of my variables was categorical. It was kind of a nightmare. So this is helpful to go through this. I do want to come up with criteria. What are we looking for in a plot? Why do the other plots fail? Why do the other plots fail? They don't plot the model fits. Okay, so when I think about a plot, like, to me, the king of all plots is a scatter plot. It's fantastic. It's amazing. Because it plots the raw data all at the same time, so you can see if your model fits, and it plots some visual representation of what the model is doing. And so you can see here's what's observed, and here's what the model implies. And it's perfect. They don't fit both the observed and the model implied. Okay. Now let me think about some of these other plots. So an association plot, they fail the interocular test. Okay, what do I mean by that? I think this was a quote by William Cleveland in his book, Visualizing Data. He was extolling the virtues of plots, and he said the best thing about plots is they pass the interocular test. And what is the interocular test? It is a visual representation of data that smacks you right between the eyes. Or in other words, you look at a plot and you know exactly what's going on. You don't have to like do mental gymnastics to figure out what's going on. And that's why scatter plots are amazing, because you can instantly look at a scatter plot and know exactly what it's saying. Let me give examples of this. So like an association plot. And that's the default right now. If you're plotting two categorical variables in FlexPlot, it's going to use an association plot. And every time one of those comes up, I borderline panic because I'm like, I have to do so much mental gymnastics to interpret what's going on here. So why don't I like association plots? Because they're mental gymnastics. Why don't I like bar plots? Similar reason. Sample size. They don't communicate sample size very well. Because with bar plots, you could either show proportions, which don't communicate sample size, or you could communicate the counts, which do, but then you get these massive differences, and it's really hard to tell what's going on, and they're not, like, standardized. Like, let's say one of your variables is extremely rare, like the probability of dying. So here's what I'm talking about, where, like, you've got such a huge sample size difference that it kind of overshadows what's going on over here, and sometimes it makes it really hard to see the patterns that are existing in the data. So we've got to do something about that, like bar charts not scaling to within group sample size. Okay, and let's look at the other plots and why I don't like them. Mosaic plots are just weird. They're really hard to interpret. And I think as we go, we'll probably learn some other criteria for what we're looking for. But we definitely want a plot that shows the observed and what's implied by the model, and they should not fail the interocular test. They should be very easy to interpret, and they need to communicate sample size information very clearly. So that's what I'm looking for. So I think the first thing I'm going to investigate is DHARMa. Okay, let me explain why I'm looking at DHARMa residuals. what this package claimed, I learned about it several years ago and I just haven't had a chance to look at it yet. But what they claim they can do is, regardless of whether you have a logistic regression or a Poisson regression or a gamma regression, or basically it doesn't matter if your residuals are not normally distributed, it's able to produce diagnostic plots that behave like normally distributed residuals. And that seems like magic to me. So I'm trying to figure out how they do that and whether it's just snake oil they're trying to sell me. Okay, so here's the important part right here. DHARMa aims at solving these problems by creating readily interpretable residuals for generalized linear mixed models that are standardized to values between 0 and 1. Okay? And that can be interpreted as intuitively as residuals for a linear model, which would be very nice. This is achieved by a simulation-based approach, similar to the Bayesian p-value, or the parametric bootstrap that transforms the residuals to a standardized scale. The basic steps are, okay, this is what I want. Simulate new response data from the fitted model for each observation. Okay. Okay. All right, so I think I know what's going on. So it's going to use the x-scores, and from those x-scores, it's going to simulate a bunch of responses. And in this graph that they have here, they're simulating something that is like positively skewed. So it's probably not a normal distribution. Maybe it's a gamma distribution or something like that. So the actual value that was observed in the data set was about a 2.5. But the simulated values, the vast majority of them, were less than 0.5. And so what it's going to do is it's going to figure out where that 2.5 falls on the probability distribution. So it's saying right here that it ends up being in the 90th percentile. So what it's going to do is it's going to, I think, convert that 2.5 to its percentile, which is 0.95. So that's how they get everything ranging from 0 to 1, is it's going to get a cumulative density function for every single observed value. Okay, so they're basically saying, all right, if we assume that the model is correct, then what should happen is that the cumulative probabilities for every single individual in the data set, some of them are going to be really unusual, some of them are going to be really commons, and they're going to have anything in between. So what should happen is, if the model is correct, we should see a uniform distribution across those cumulative probabilities. That is a brilliant idea! Ha! I love it. Okay, I don't know if this applies to what I'm trying to do yet, but that's a really cool idea. Okay, that means that we expect the distribution of the residuals to be flat regardless of the model structure. Yes, you do. If the model is correct. Oh, cool. So if it's not correct, then it wouldn't follow a uniform distribution. Okay, so let me think about that. Could we... Ooh. I think we might be able to use this, maybe. Okay. Okay, so here's my idea. I don't know if this will work. But if it does, this is great. Okay, so my idea is that we fit a logistic regression model. So basically, and that's one thing I sidestepped, is that I am going to use logistic regression to model the relationship between a categorical outcome and a binary outcome. Why logistic regression? Just because it fits within the general linear model framework. I don't like chi-squares because it doesn't fit within that generalized linear model framework. So if we fit a model between a categorical predictor variable and a binary outcome, and then what we do is we convert that 0, 1 to a cumulative distribution, then it's going to convert that 0 or 1 value to a probability that represents a cumulative distribution. I just realized a problem, though. Ah! Dang it. I just realized the problem. Okay. I'll just explain what the problem is. The problem is that these are residuals. I don't want to visualize the residuals yet. I want to visualize the observed values. So initially, this seems like it's not getting me what I want. But, oh, got to get out the iPad. Be right back. So I think this still might work because what is a residual? A residual is equal to y minus y hat. It took me a little bit to realize that the result of the cumulative density function was not equal to the residual, but you then had to apply some sort of transformation to convert it to a residual. And one simple transformation you could apply is just subtract whatever that cumulative probability is from 0.5, and that'll give you a residual. So let me do this again. So the residual is equal to observed minus y hat. And so if our percentile is equal to 0.6, then that means our residual, we're going to subtract that from 0.5 or subtract 0.5 from that, whatever. Let's just say it's 0.1. So then our residual would be 0.1 is equal to observed minus y hat. Again, using the same logic, we get the y hat from the logistic regression, so we get the observed minus y hat, and let's say that it predicted a, 0.5. So then we could solve for observed, and that would give us 0.6. Well, that is a way to convert the 1, 0 to an observed if the model is correct. I don't know if I like that. Because that doesn't fulfill the first criteria. Remember, the first criteria, we wanted to have a plot that shows the observed and then that which is implied by the model. And here we're kind of doing almost the opposite. We're taking the model and saying, if the model is true, this is what your observed would be. That's not gonna work. Oh, and I just realized we're gonna have to eliminate a lot of these. I don't think, I think this eliminates Jesus sucks. This eliminates the majority of the really cool ideas that I had. Because there's the Bayesian predictive checking, or Bayesian posterior predictive checks. So that essentially eliminates DHARMa and Bayesian thinking. And that's a common technique in stats that you say, all right, if the model is true, in fact, that's what null hypothesis significance testing is we assume that the model is true and then estimate the probability of obtaining what we actually obtained. So it's a common tactic, but it doesn't meet my criteria. And that criteria is important. It's super important. Because when you make a plot, you want to make sure that the model you're estimating actually fits the data. And if we are using the model itself to generate the observations, it totally fails. Totally fails. Ugh. Part of me wants to try it anyway. Because I am curious, what happens. I'm just disappointed that that's not going to fit my criteria. But you know what? I'm going to look at the plot anyway, and then maybe I'll learn something from it. So give me a second. I'm going to step into R and come up with a DHARMa-like plot for categorical on categorical plots.
And now, a word from our sponsor.
Yes, tell me how you're feeling right now.
I don't know, I'm just depressed all the time. I feel like I have no meaning in my life. And what's the point anymore? You know what I'm saying?
Oh, I see.
I don't know, Doc, do you have any suggestions?
Well, the only suggestion that the only surefire suggestion that I can give is to take a statistics class from Simplistics.net.
Wait, what? Take a statistics class? How would that help with my sadness, depression, and lack of meaning in life?
You jest. The answer is obvious.
That's right. You can take a Simplistics class from me and fulfill all your childhood dreams-ish. I offer both live classes where you get to interact with me through Zoom and on-demand classes where you get to learn at your own pace and stuff. And I won't go as far as saying that some of the most famous celebrities that exist think my classes are the best thing in the world, but I also won't say that that's not true, if you catch my meaning. So visit simplistics.net and take a class from me. Hope to see you there. Now, back to your regularly scheduled program. It's not gonna work, like, at all. And it's not just for the reasons that I thought. It's not gonna work at all. I feel dumb for not seeing this. Like, duh, it's not gonna work. Because for your categorical variable, you only have 3 levels, which means that you're only gonna have 3 distinct residuals. Yeah, if you share identical x values, you're going to have identical residuals. And there's no way around that. That was a complete waste. That's why it's the Holy Grail, man. This is why it's so hard. And I thought I was like being super clever by, nobody's thought of this DHARMa residuals before. And maybe that's true. Certainly outside of the box thinking, but at the end of the day, you still have the same problem. So that was a totally fruitless avenue to explore. All right. Back to the drawing board it is. And it's communicating sample size because each dot represents a person. Oh!